Hey guys, Buildzoid here, and today we're going to be taking a look at how I repaired this here Galax GTX 980 Ti Hall of Fame LN2 edition. Now, I bought this card in not working condition from a fan of the channel, and the reason that I bought this card is very simple. This thing has a 16-phase Vcore VRM with the standard Galax Hall of Fame output filtering configuration, as in there's a lot of capacitance and there is a, pretty good, good mix of capacitors, and that's the most hand-wavy way I can describe the output filter, but basically this may very well be one of the best Vcore VRMs you can get on a GTX 980 Ti, and so I want it in my GPU collection. Because, yeah, I collect GPUs with interesting power delivery. And as far as GTX 980 Ti's go, it really doesn't get much more interesting than this. Unfortunately, this PCB is also very, very rare, because as far as I know, it was only available for a, LN2 overclocking event organized by Galax, which is rather unfortunate because, personally, I don't find, as a collector, I do not value the rarity of the things that I collect, right? I have, there are certain GPUs in my collection that are actually, straight up mass-produced, they're not rare, but they just have interesting power delivery, so they're in my collection, or good power delivery, so they're in my collection, right? But then you get cards like this, where it's like, yeah, I wish all 980 Ti's had a VRM similar to this, but most 980 Ti's come with the reference PCB, and the reference 980 Ti PCB is kind of trash. So, anyway, yeah, so obviously I want one of these, because this is just a really, really, this should be a really, really good Vcore VRM, and I want to measure it, and yeah, luckily for me, the reason this card wasn't working was a relatively simple fix. So let's get into what was wrong with it and how I fixed it. So the first thing you do with any GPU that doesn't work is you don't try to turn it on, because depending on what kind of failure the GPU, what kind of component failure is on the GPU, every time you power cycle it, you might be making it worse. Or, if you're really unlucky, certain component failures, every time you power cycle the card, run the risk of killing the GPU core and or the memory chips permanently. So yeah, if you're buying dead GPUs to repair them, or if you have a GPU that doesn't work, you don't try to turn it on repeatedly. Especially if it's causing weird power issues. If it's not letting the system turn on, you definitely don't keep trying to turn it on. So anyway, I didn't try to turn this card on. I started off by checking for short circuits. Now, this is an NVIDIA GPU, so checking the 12-volt power distribution for short circuits is very, very convenient, because we have all these lovely shunt resistors, and each of these corresponds to one of the 12-volt power inputs. So this one is for this 8-pin, this one is for this 8-pin, this one is for this 8-pin, and this one is for the PCIe slot. Actually, I'm not 100% certain that this one is for this 8-pin, but yeah, one of these is actually for the PCIe slot, which is why we have 4 shunt resistors next to 3 power connectors. And you might be wondering, wait, why is the PCIe slot shunt resistor all the way over here? Well, that's the magic of multi-layer PCBs. You can just kind of run things really far for weird reasons. It's like a lot of other GPUs would just put that shunt resistor and the input filtering inductor right next to the PCIe slot, but Galax, for whatever reason, decided to run the 12-volt power all the way over to this area and then go through the shunt resistor and the inductor. So a bit of a sort of weird layout choice, but ultimately, it is pretty standard practice on NVIDIA GPUs to have, at least one Vcore VRM phase running off of the PCIe slot. There's, reasons for that we're not going to get into. So they would have, Galax would have ultimately been running the 12-volt power into this area of the board. They'd be dragging the 12 volts from the PCIe slot over into this area anyway. Or at least for the memory power delivery, they'd be dragging it into this area. So kind of makes sense that, we do have all 4, it doesn't really make the layout of the board that much more complex, because they would have been running 12-volt power over here anyway. But yeah, a lot of other cards would have just left that shunt resistor and inductor nearer to the PCIe slot for like layout convenience. But evidently Galax had plenty, like this board. I don't know how many layers this board has. So I guess they just had plenty because they did decide to put the shunt and the filtering inductor for the PCIe slot all the way over here. Anyway, so to check for the short circuits on 12 volts, it's really simple. You just measure from either side of the shunt resistor to a ground, right? Now, I don't usually use screw holes for ground because a lot of the time, especially if you're like dealing with older cards, the screw holes will be quite heavily oxidized. And so getting like good contact between the multimeter probe and the screw hole ends up being kind of a pain. So I usually go for like this notch on display ports. Yeah, you just stab the probe into that, and that tends to give you a very good, reliable connection to ground, because the outer casing of display ports is soldered directly into the ground plane of the GPU. So I like to use that for that connection. The other benefit of like using that notch is that the probe isn't going to like slip out and go anywhere, right? Because like technically like one side of these multi-layer ceramic capacitors is ground. But if you're not paying attention to the probe and your probes aren't super sharp, then, you know, you might accidentally, like, slip the probe and then knock a capacitor off the board. And that wouldn't, like, you know, well, if you just knock a capacitor off the board, it probably won't kill the card, but, like, you're doing more damage for no good reason. So I like to go with, yeah, DisplayPort casings as my ground, like, as where I get my ground from, because that's just really convenient. I also occasionally use the display, like, the actual PCIe bracket itself, but I found that on some cards, the PCIe bracket actually doesn't make good contact with the like grounding points on the board itself. That's mostly an issue on like really, really old cards. But yeah, like the bracket itself isn't always that great like place to get your grounding from, because it isn't actually soldered into the board, right? Whereas this is a piece of metal that like you can literally see like it's soldered into the board right there. Whereas the bracket is just like bolted to the board. So anyway, yeah, so that's where I like to get my ground reference from. But honestly, like, yeah, you could use screw holes. You could use this ground point over here. I think actually, I'm not sure. I don't remember the pinouts of PCIe connectors, so I'm not going to give suggestions on that. But anyway, so, you know, one probe on a ground point and the other probe on either side of the shunt resistor, and I just check for the resistance. And so this resistor over here measured somewhere between 100 kiloohms and 1 mega ohm. One of the issues with measuring like the like 12 volt power on GPUs is that you're connecting that multimeter across a whole bunch of capacitors. So that resistance measurement is potentially gonna like start low and then like rise, or it's gonna start high and then drop. It's gonna be weird. But basically, if you're getting something in the like hundreds of kiloohms to like mega ohms range, it's fine, right? That tells you that there isn't a short circuit. So anyway, so this one measures like over 100 kiloohms. This one measures over 100 kiloohms. This one measures 4 ohms, which immediately tells me immediately tells me roughly what is wrong with the card. And this one also measures hundreds of kiloohms. So, you know, no short circuit, no short circuit, no short circuit. And then this right here, well, 4 ohms is the resistance of the GPU core itself. So we have a short circuit, which is connecting this shunt resistor straight to the GPU core. And this is one of those kinds of failures that, yeah, if you tried to, you know, power cycle the card a bunch of times, this could potentially seriously damage the GPU core. And, like, luckily this isn't the kind of failure where it's an automatic death sentence, like, say, memory VRM failures tend to be. Like, a lot of the times if one of your high-side MOSFETs in the memory VRM dies, it'll just insta-kill all of the memory chips and the GPU core. For whatever reason, Vcore, like, short circuits from 12 volts to Vcore don't tend to be quite that efficient at destroying things. But they are still very dangerous, and you don't really want to be power cycling a card where you have 12 volts connected straight to the GPU core. That's really bad. Now, another measurement that I took is actually from this shunt resistor to one of the Vcore VRM inductors, and that measurement showed 0 ohms, which isn't surprising because, you know, from the 4 ohms, it's like, well, that's the resistance of the GPU core, so probably one of the high-side MOSFETs in one of the Vcore power stages is just completely shorted out, and there should be a 0 ohm resistance between the output of the Vcore VRM and our shunt resistor. So that's kind of that. There's a dead power stage on this board. I need to figure out which power stage is dead and then remove it. Now, the annoying thing here is there is no measurement you can take, there's no measurement that you can there's no convenient measurement that you can take to tell you which power stage is broken. Because all of your power stages are in parallel, all of your inductors are in parallel. So let's say, hypothetically, this power stage over here is the one that has the short circuit, and I decide to because I've seen people do this, which is why I'm pointing this out. So you decide to measure the resistance over here, right? You measure from here to the shunt resistor that's shorted out. What's going to happen is your measurement is basically going to go through this inductor, through the dead power stage, to the shunt resistor. So you're still going to get 0 ohms, right? If you decide to check from like this inductor over here, it's going to go through this inductor, right? It's going to go through this inductor, then it's going to go over to this inductor, through that inductor, through the dead power stage, back to that shunt resistor. Also 0 ohms. So basically at this point, there's actually no way to you can't just measure from the, you can't measure from the switch node of a phase to figure out which phase is shorted out. That just doesn't work because they're all in parallel with each other. So right now, they functionally all look like they're shorted out. My preferred method of figuring out which phase is shorted out is to start lifting inductors. And you don't actually have to remove all of the inductors, but on this card that unfortunately isn't viable because getting 2 soldering irons around one of these inductors isn't possible because this gap between the capacitor and the inductor is just simply too small. So yeah, that method of this is what with inductors like this, you can actually just lean them over. You can just desolder them on one side and then lean them over. But this style of inductor, you can't technically brute force them into bending like that, but it's not fun. So I'm not doing that, especially not on a card this rare. Yeah, I'm not going to be abusing the inductors to figure out which power stage it is. Ideally, I would come in with 2 soldering irons and just desolder the inductor, but like I mentioned, the gap is too small, so that's not happening. Using hot air on the inductors is technically possible, but in this close proximity to the capacitors, that would cook the capacitors. Because the amount of heat you need to desolder an inductor is just ridiculous. These things are a lot of metal, they're quite heavy, they absorb a lot of heat. And also this is a very high layer, this is a rather high layer count PCB designed to handle a lot of power. Hot airing the inductors off of this thing is probably going to kill the capacitors. So, not an option. So basically my preferred method of just figuring out which subset of power stages is connected to the shorted out one and then desoldering inductors until I find the one that's shorted out, not an option. As for how you would actually figure out which set of power stages is actually shorted out, because, yeah, sure, if you measure from the inductors, they all look like they're connected together. They're all connected together and they all look shorted out, but they don't all get their 12 volts from the same place. So what you can actually do to narrow down which set of power stages is suspect is you can just measure across the input filtering capacitors next to them. Right? So, I don't actually remember the measurements for all of these at this point, so, but what I do remember is that this one was this capacitor over here was shorted out. I think also this one and maybe this one. I think it was 4 power stages that I was okay, these are all connected to the same shunt resistor. So Anyway, yeah, so I figured out that there was like a set of power stages that are connected to the shorted out inductor, and that I mean to like that, like there's a like a specific set of power stages that are of which one is shorted out to the shunt resistor. Oh boy. Because the thing is, again, like they're in parallel on the 12 volt side, so these all look shorted out, right? Like like however many, like all the power stages that get their power from this from this shunt resistor, they all look like they're shorted out, right? Even on the 12 volt side. Whereas the other shunt, like the power stage, like say this power stage over here, this one doesn't look like this capacitor isn't shorted out. It has the same measurement as, you know, measuring from the shunt resistor to ground did. So that's hundreds of kilo ohms there. But the capacitor over here, that one was measuring 4 ohms, right? So we can sort of go around with these capacitors and find a couple of them which are all measuring 4 ohms and go like, okay, it's got to be one of these power stages. So that narrows down the, you know, search quite a bit. Now, one option that you have with certain types of power stages, if you can get a public data sheet, is you can measure the gate low and gate high pins. These don't have public data sheets, so that option is also not, you know, an option for figuring out which power stage on this card is broken. So I had to resort to the potentially least reliable method of trying to figure out which power stage is broken, which is just looking for visual clues and, you know, hoping that I got it right. Because unfortunately, or, well, depends on how you look at it. Sometimes you'll have a power stage that melts down so hard that, well, you can tell which one failed from a mile away because most of it might be missing. Unfortunately, in those scenarios, you also usually have significant PCB damage, so that's not ideal, but at least figuring out what part of the card died is really easy when there's a crater there. Yeah, or sometimes you'll get power stages where you have like a very clear indication that, oh, this is the power stage that burnt out. With this card, there was a visual indication as to which power stage burnt out, but it was rather subtle. It's this, which at a glance might look like just like bad soldering quality from the factory, but that's not what's going on at all. Also, we do have something that looks like it might be ejected material, like material ejected from inside the power stage, but this could also be like thermal pad residue. So, yeah, not 100% certain about what this gray stuff is over here. But that solder ball, that is very suspicious. Because while it might look like poor, you know, manufacturing quality, what this actually is the end result of the high side MOSFET in this power stage getting so hot that it melted the solder, and then the solder came out the side. That's what that solder ball is. Because how the power stages are supposed to look is like something like this, or this, and actually I have more angles. Yeah, so here we have an angle that's like much more clearer. Like this is what a good power stage looks like, right? Or something like that, or something like that. And then we have this like solder ball over here. So, like, I know for a fact that this power stage is in that like set of power stages that has the shorted out input filtering capacitor next to it. This one also has this very suspicious blob of solder next to it. So I decided, okay, I'm just going to desolder this one. Because with all probability, it is this one. Right? And so I desoldered it. And to desolder the power stage, I use a hot plate to preheat the board. That was set to 140 degrees Celsius. I also use flux. The flux that I'm using for this is CHIPQUIK SMD291. The tape you see on the capacitors, this is kapton tape, and the reason why I'm putting that up against the capacitors is that capacitors really don't appreciate being in like 300 degrees Celsius, or, well, in this case I was using 370 degrees Celsius hot air. Yeah, capacitors don't particularly appreciate being exposed to very hot air for extended periods of time. It degrades them, and actually if you roast a capacitor with hot air long enough, it'll actually just like pop off the board. Quite violently, potentially, as you'll just melt the insides, because these are solid polymer capacitors, so there's no liquid inside them. But if you heat them up enough, their solid insides stop being, well, solid. So yeah, the tape is basically there to act as a bit of a like thermal barrier to prevent the capacitors getting directly exposed to the hot air. And the kapton tape is like specifically designed to withstand very high temperatures up to like 350 degrees Celsius or something. So it's literally designed for this kind of like heat shielding application in soldering scenarios. Um, Anyway, so that's what the tape is for, is just to protect the polymer capacitors, because, yeah, they don't really appreciate being blasted with hot air, but there's no other way to get that power stage off. So, yeah, so that's the prep, is preheat the board with the hot plate set to 140 degrees Celsius. And then for the actual hot air, I use 370 degrees Celsius on the hot air. And yeah, the power stage came off nice and easy. Well, more easily than it does on a 3090, but not the easiest. Like, again, depending on how many layers a PCB has and what kind of power delivery it's designed for, pulling components on some cards is significantly more difficult than pulling components on other cards, but this really wasn't too bad. Like, especially compared to something like a 3090, this was actually quite easy. And luckily for me, the dead power stage didn't weld itself to the board, so that's nice. I don't have to reconstruct any pads. So anyway, dead power stage is off. At this point, I already go and make a check if the short circuit is gone. So again, I just retake that measurement of like here to an inductor, and it's like, oh, now, now we get hundreds of kiloohms. Because, well, we've removed the shorted out power stage. And also, if I measure from the shunt resistor to ground, again, it's hundreds of kiloohms because that shorted out power stage isn't there anymore. So, but like the reason I make this check is because I wasn't 100% certain that, like this is definitely the dead power stage. The fact that there's that little, suspicious ball of solder next to it, I'm like 99% sure this is the dead power stage, but I'm not 100% sure. So I did want to make, did want to check that I did in fact pull the dead power stage and not just some random power, like a power stage which had like some weird soldering residue from the factory, which it really shouldn't. Like, I don't think I've ever actually seen a power stage soldered so badly that there was like a ball of solder sitting next to it. But it's like, I want to be 100% certain. So we check if the short circuit is actually gone right after pulling the power stage, not after replacing it, because what if you screw up the replacement and then the short circuit is still there, right? Like if you short the pads when replacing the power stage, and then it's like, yeah. So I make a check that the short circuit is gone. The short circuit is gone. And so then I proceed to go and look for a donor board because, yeah, you can't buy fresh IR3555s as far as I know. So I ended up sourcing a new I ended up sourcing a replacement 3555 off of a dead GTX 1080 Ti, I think. The reason I say dead, I think 1080 Ti is because I only have the Vcore VRM portion of that card. I don't have the rest of it anymore. I think it was a 1080 Ti. Anyway, so yeah, also here you can see the bottom of the dead power stage, and honestly, this thing like other than the fact that it was shorted out, like it looks completely fine. So yeah. Anyway, oh, I guess that like the high side MOSFET in this power stage like completely melted down and was a 0 ohm short circuit, but the rest of the power stage like was probably actually still okay. Well, the driver circuit might be dead as well, but anyway, like it didn't weld itself to the board. That's the main thing that I'm happy about, is like the board wasn't damaged by this power stage failure. Anyway, and here's the new replacement 3555, because it's obviously not new. I pulled it off of a dead GPU. So yeah, but here's the wait, are we even looking at it? Man, I can't even tell which one it is that I replaced. So yeah, here's the new 3555 replacing the old one. And again, to replace it, I just use the hot air at 370 degrees Celsius. Though the way I do replacements is I'll actually I don't put the power stage on and then heat the power stage into like attaching itself to the board. What I do first is I actually heat the pads until like I can poke at the solder with my tweezers and see that the solder is liquid, right? And the reason I do it this way is because I really don't want to like cook the power stage when reinstalling it. So I want the board to basically be at the melting temperature of the solder when I put the power stage on, right? Also, obviously, I applied more flux. Yeah, this flux is quite spent at this point. So I apply more flux, and then I heat the board to the point that, like, with the hot air, I heat the board until like I can start pushing the solder around with my tweezers. Mainly on these big pads, like this goes off to the switch node, so that melts really quickly. But like we have, I think this is a ground pad, and then these are like 12-volt pads. So these, there's a substantial 12-volt power plane hanging off of that. So this takes quite a lot of heat to get up to like solder melting temperature. So yeah, I just heat the pads until I can see that the solder is liquid, and then I put the power stage onto the board. I don't like start with the board at like, it wouldn't be cold because again, I am preheating the board, but the board would potentially be starting at a temperature of like say 100 degrees or 120 degrees instead of 190, right? And obviously if the board starts at 190, I don't have to cook the power stage that long with the hot air to get it to, attach to the board. Because yeah, like it's already not ideal that I'm like recycling a power stage. Because the power, like the components aren't really designed to be moved around a bunch. I've so far not actually had a like recycled power stage fail on me, but like the manufacturers recommend that you don't like reuse your SMD components, though that might be just because they want to sell you more SMD components for all I know. But either way, yeah, so I do my best to like minimize how much I am cooking the power stages and just cook the board more. Because, well, if the solder isn't melting, then evidently the board isn't that hot, is it? Right? Like, sure, I might be, hitting it with air that's at like 370 degrees Celsius, but like until the solder melts, the surface temperature of this area of the board literally cannot be more than the melting point of the solder because the solder isn't melting, right? So that's my logic for that. It might be wrong, but yeah, that's sort of my thought process is like heat the board until the solder melts, then put the power stage on. Don't take a cold board and then try to cook the power stage into place because that, like, I've never actually tried that, but I don't really want to, test my luck with like how long like a power stage will tolerate being heated on a cold board before it becomes a major problem. So yeah, I basically want to minimize the heat exposure for the power stages. So anyway, that's the process I go through to actually reattach the power stage, and then once it's in place, it's done. Like at this point, you just check for short circuits again, right? We want to check that 12 volts isn't shorted. I want to check that this capacitor isn't shorted. That this, like, I check the resistances on like all of the components around the power stage. I think this is actually another input filtering capacitor, and this thing I think is like bootstrap or something. But anyway, so I check the resistances on all of the supporting components, and I compare them to the resistances on a known good power stage, right? So I would like, for comparison measurements, I would like take this power stage over here because this power stage isn't powered off of this shunt. It's powered off some other shunt. I don't know which one. So, I take measurements of all of these, and then I compare them to the measurements of the power stage that I replaced. And if the measurements are close enough, which they were, then I go and see if the card actually turns on. And the card did turn on, and it did run Firestrike, so fixed. Yay. And I made this video entirely unnecessarily too long, but yeah, especially because this is literally just a power stage replacement. I didn't even have to like rebuild freaking switch nodes or anything, but yeah, anyway, I don't know. I'm not reshooting this because I keep trying to reshoot it and telling myself, oh, I didn't need to leave all that extra stuff in. And then it's like, and then I try to reshoot it and then I go, And then I add that add the information in anyway. So evidently, I should just give up on trying to make the video shorter. So yeah, I'm actually really pleased with my soldering job on this power stage, because this is, I think, the cleanest one I've done. Because yeah, I have other, like, I've replaced other power stages on other cards at this point. And actually, there's one card where I literally replaced every single power stage because I had this idea that I was going to upgrade the power stages on it, except I used power stages that weren't compatible with the footprint on that card. So then I had to take so I had to re-replace all of the power stages with like compatible ones, which was a fun experience. But at least I got great practice on placing power stages with replacing power stages with hot air. That card does work. It doesn't look, I don't think it looks quite as clean in terms of the soldering job as this does. So, yeah. Anyway, that's how I fixed a Galax GTX 980 Ti Hall of Fame LN2 edition. And, yeah, I don't actually have any immediate plans for the card, because I wasn't really expecting to get my hands on one of these anytime soon. So now that I have it and it works, it's like, what do I do? I mean, I did mention earlier that it's like, oh, I want to take VRM measurements, but I also want like comparison measurements for the other 980 Ti's that I have, which I don't have that data, so it's like, and then maybe like come up with some test methodology, and yeah, but anyway, that's it. I managed to like fix a GTX 980 Ti Hall of Fame, and honestly, I'd say this is probably the best soldered power stage I've ever soldered. Yeah, as in terms of like it's very clean. It's not a mess. It helps that the that the board didn't get damaged when the power stage died. That helps a lot with the soldering quality. So, yeah. Anyway, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store where you can pick up shirts, hoodies, posters, stickers, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. And that's it for the video, so thank you for watching, and goodbye.